The human hand is a complex integrated system with motor and sensory components that provides individuals with high functionality and elegant behavior. In direct connection with the brain, with 35 muscles, 22 articulations, and more than 17,000 sensors in the skin, the hand is capable of performing countless actions. Its versatile prehensile abilities allow for tasks ranging from the fine digit manipulation to the handling of heavy objects. Not only, the hand is a marvelous cognitive instrument for sensing and exploring the surrounding world, as well as an instrument for non-verbal communication. More than 2,000 years ago, fascinating by this amazing limb, Aristotle claimed, "The hand is the tool of tools." The skillful motor and sensory functions of our hands cannot be given for granted, as traumatic amputations or neurological injuries may severely compromise them. In the European community, every year there are 2,000 new hand amputations and about 7,500 new spinal cord injuries, of which a significant percentage affect hand function. Deprivation of hand function causes a severe mental and physical debilitation. Functional substitution as well as recovery of the sensory motor capacities of the human hand represents one of the major goals in applied neuroscience and bioengineering, faced worldwide by scientists and engineers. Among these efforts, WAY, acronym for Wearable Interfaces for Hand Function Recovery, is a collaborative project funded by the European Commission under the 7th Framework Programme for Research and Technological Development. WAY addresses these technological and scientific challenges to enable patients with amputation or neurological injury to improve their autonomy and quality of life. WAY is coordinated by the Scuola Superiore Sant'Anna in Pisa, Italy, and involves 6 partners from 6 different countries in Europe. WAY faces 2 different clinical scenarios. The first one focusing on upper limb amputees fitted with a dexterous hand prosthesis. The second one targeting individuals with limited hand function and sensibility, due to SCI, whose motor and sensory functions could be recovered by means of wearable robotic exoskeleton. The objective of this 44-month project is to restore a physiological bidirectional link between a patient's brain and a hand-assistive device, like a robotic hand prosthesis or a robotic hand exoskeleton, without the need of surgery. This is made possible by developing new wearable interfaces between the body and the assistive device, able to decode movement-related user intentions and translate them into robot hand function, as well as convey tactile stimulation to the patient recorded by sensors in the hand-assistive device. For the first application scenario, WAY researchers aim to restore dexterous motor function and tactile sensory feedback equivalent to that of the human hand after amputation. That is one of the major goals in rehabilitation engineering. Ideally, a system like this consists of 2 components: the dexterous mechatronic hand with artificial tactile sensor, a physical replacement of the hand, and the human-machine interface, a system that bridges the artificial hand to the brain in a bidirectional manner, thus able to decode the user's intentions into hand motion and convey sensory information picked up by hand sensors back to a person, a way to interface with the brain. The challenge is to implement such a prosthetic system in a physiological manner that is natural enough to control, sense and feel the prosthesis as a part of our own. Today, the most reliable technique remains the use of Electromyogram Emg, the electrical activity produced by muscles when they are voluntarily contracted. These myosignals can be recorded by surface electrodes to control the movements of an electromechanical prosthesis. However, this type of control can be slow and unintuitive, also due to the fact that the sensory feedback component is completely missing. Mirko Menini, a 32-year-old man, got his right hand amputated in 2009 due to a work accident. He is among the first subjects to test the new prosthesis developed within the WAY project at the Scuola Superiore Sant'Anna. The hand he is controlling is one of the most advanced multifunction hands and was developed at this institute. Mechanically, it allows most of the grip patterns useful in activities of daily living, and its fingers host sensors to detect touch. The important thing, however, is the control interface based on 4 wearable electrodes in contact with the stump inside the socket. A sophisticated algorithm allows to map the muscular patterns associated to 4 grips to the equivalent movements in the hand physiologically. The grip force is also modulated by Mirko's muscular strength in a way he can decide whether to gently grasp or crush an object. The novelty is in the way the signals are processed. The control output is practically insensitive to arm movements, which allows Mirko to operate the multiple grip patterns in space in a close to natural manner. Researchers believe that the system is reliable and could operate in real-life scenarios and not just inside a laboratory. As regards to the sensory feedback, it stands to reason to believe that this would improve the ability to grasp and manipulate objects. However, this was never demonstrated by scientists in practical scenarios. To tackle this, WAY researchers followed a novel approach called on the Discrete Event-Driven Sensory Feedback Control, or DESC, model postulated by Prof. Benedin from Umeå University, Sweden, key partner in WAY. This model posits that motor tasks in humans are organized in consecutive phases, delimited by specific mechanical events, which are signaled to the brain by means of discrete sensory events. For example, in a pick and lift task, the contact or breaking of contact of digits with the object are important events that are signaled to the brain by means of the biological sensors in the fingertips. WAY researchers developed special gloves that can be worn on conventional hand prostheses, as the one used by Roberto in this test. The special thing is that these gloves include touch sensor on the digits and stimulate the individual by means of miniature vibrations on the cuff arm, following the desk approach. For the second application scenario, WAY researchers aim to assist motor function and tactile sensory feedback to individuals with limited or no hand function and sensibility. This is a very important debilitation which can be caused by spinal cord injuries. WAY target this condition using a robotic exoskeleton with artificial tactile sensors to assist the movement of the hand, and a wearable brain-computer interface, a BCI, able to decode brain signals and launch the appropriate motor command to the hand exoskeleton. Wearable BCIs are largely desirable because they do not require surgical procedures or brain implants. However, it is very challenging to decode motor-related brain signals from outside the scalp. Frank Ruprecht is a 53-year-old man with an incomplete spinal cord injury. Because of this, he is unable to control the movements of his hand properly and to feel the sense of touch. The hand exoskeleton developed by engineers at the Scuola Sant'Anna could support and assist his movements due to miniaturized motors and self-aligning mechanism. Frank is wearing the thumb index exoskeleton and is controlling 3 different grasps by a remote control. The whole system is fitted on a wheelchair at the Guttmann Institute in Barcelona and is powered by a battery. The exoskeleton allows Frank to sign with his own hand again. As for the first scenario with amputees, engineers developed a glove with touch sensors that detects contacts with the objects and provide tactile stimulation on sensitive body parts. The tactile stimulation is still based on the desk approach. This instrument holds the potential to be an effective neurorehabilitation instrument for patients after spinal cord injuries and is currently being tested at the Guttmann Institute in pilot studies. The substitution and rehabilitation devices developed within WAY are of potential market interest And Össur, Iceland, a leading company in these fields and partnering in Way, is exploring ways for making such devices commercial products. Besides developing novel and practical assistive devices for the disabled people, Way is contributing to the BCI community in a broad sense by making large datasets of electroencephalographic signals open access. A total of 15 gigabytes data from healthy subjects while performing hand manipulation tasks of realistic complexity was collected at Umeå University, Sweden, and made available through the Nature Scientific data. The dataset was designed to allow scientists from the artificial intelligence and BCI communities to test algorithms that decode the intention and current actions from brain activity in humans, while performing a simple grip and lift task, engaging the thumb and index finger. Experts in machine learning from the Scuola Universitaria Professionale della Svizzera Italiana, Lugano, already worked extensively on this dataset, and interesting results are forthcoming. The hope is that this public dataset will foster novel scientific knowledge on the brain functioning as measured by BCIs.
The Way project produced a number of results, both in terms of scientific papers and in terms of exploitable results. However, the need for assistive devices with natural control and sensory feedback is still huge, so there's still much to do. The goal is to develop integrated devices that can be brought outside of the lab, which integrate both the sensory part and the control part.